let's begin with a black hole so that we have this as an introduction. There was an article that came out that says scientists closely examined stars wobbling, and they determined that there must be a massive invisible partner influencing its trajectory. Okay, so I want you to see the language that they use. There must be a massive invisible partner. Yeah, they speculate, they infer that whatever's happening is being caused by an unseen, invisible, untouchable partner. That's the issue. And so they're assuming that there is a massive partner because they think that the only way you can affect the visible object's motion is through gravity, through mass. It never occurred to them that they could also influence it with magnetic fields, so to speak, whatever those are. But magnetism is a very powerful force out there in the universe, and they never at all consider it for anything. They just look at mass and gravity. And that's where the problem starts, okay? What they do something like this. They go out there and they look for filaments. And this is, again, these are really not pictures. These are not real pictures or images of the night sky. What they are really is computer simulations of what they see out there. They make it so that you can see what they kind of see through their scopes, but they don't see this at all. What they have is all this radiation coming towards them, and they build these maps, and then they computerize them, and this is what they feed you. And so you say, oh, look what the telescope saw. No, you're not looking through a telescope there. But the point is they go all the way in there, you can see there, and they're going to reach to a region where they see some action. They say, oh, it's a black hole in there that's doing all this. And, it's just inference, okay? And lots of people are involved in all this stuff. And by the way, here you have one paper, and there's, I think, 66 people involved in writing this paper because it's a group that is spread around the earth, and they all put their names on the paper. So all these people are receiving money to come up with all this nonsense. And I'm just giving you a drop of water. There's papers being written every day with 60, 70 people signing up on them. All these organizations out there that receive billions of dollars doing so-called research on black holes, dark matter, dark energy, Big Bang, all this good stuff out there, wormholes, And the question is, if these people are not on the right track at all, if they're not even close to reality, what are we spending all that money for? That's something you should think about, right? Anyways, that's the black hole. So what's the difference between a black hole and a neutron star, right? Or a pulsar or a magnetar? What are the differences? What are we talking about here? Well, the only difference is really how big the star was before it collapsed, okay? So it's got big, lots of mass. It goes down to zero, and it turns into a black hole. Okay? There's nothing there, no size, no volume, no shape, no nothing. Okay? It crushed all matter out of existence. But if it's not big enough, it's got a better result. It's going to reach the size of a pebble, maybe, or maybe the size of a city, as they say, right? And it's going to compress all the matter that the star had to a certain size of a city, size of a pebble, whatever, it doesn't matter really, to small size, not to zero like in the black hole. It's going to just squeeze it to a small size. And then the issue is, how did they come up with this stuff? Well, they say that those little balls or whatever is there are sending light beams to our eyes, to the earth. And that's the argument there. And so they say, oh, when they see a flash of something coming to their eyes, they say, oh, that's not a black hole, because black holes suck light in. It's got to be a neutron star or a pulsar or a magnetar. That's the way they look at it. So it's just a question of how much mass the star had before it shrunk to its final size, more or less. Okay, so here we have a neutron star. Okay, gives you an idea what the difference is between a black hole and one of these neutron stars, or pulsars, or whatever they want to call them. Neutron stars are stranger than science fiction. And that's a terrible way to start a physics dissertation. You read that, and the first thing you think is that they're going to take you down a rabbit hole. It's worse than science fiction, Jesus. And I came here to get my science shot for the week, and this person's going to talk about science fiction. Anyways, a star bigger and more massive than our sun runs out of fuel at the end of its life. Its core collapses while the outer layers are blown off in a supernova explosion. What is left behind depends on the mass of the original star. If it starts with more than 20 times the mass of our sun, it becomes a black hole, meaning it turns into nothing, right? Because all matter gets crushed out of existence because of gravity. Gravity crushes it out of existence. However, if it's roughly 7 to 19 times the mass of our sun, we are left with a neutron star. And there you get to see more or less a picture of what they have in mind. By the way, these are not real telescope images. These are just, again, computer simulations, drawings, etc. And what they show is a little ball there. It's supposedly a star, or what's left of a star, the cinder of a star. What you see there is all the atoms packed very closely together, smashed against each other so that they form just a neutron star. In other words, all the components of that star are primarily neutrons. They're very little atoms, they say. And as you can see the magnetic field there, and it also wobbles. And because it wobbles, it functions like a beacon, like a lighthouse beacon. And it just sends you little pieces of light to your eyes if you're here on Earth. Okay, that's more or less the notion they have for what a neutron star is. And then we're going to have all these variations, the pulsar and the magnetar, and who knows what else they'll discover in the future. But we have to look first, before we can understand that, we need to understand really first, what is a neutron? Because I'm saying, it crushes all these atoms and turns them into neutron. Well, what's happening here? What's happening? How do you explain that? What's the mechanism? What are we trying to explain here? So we start by looking at the proton, okay? And here it is. That's what a proton looks like according to math, okay? The mathematicians, they say it's 2 up quarks, 1 down quark, okay? Turns out the neutron's going to be in reverse. It's going to be 2 downs and 1 up. That's essentially the difference between them. Okay, here you get a picture more or less of what a neutron might look like. This is how they imagine it. And I just want you to focus on something, and that is it's got a sphere there. And that sphere is called the neutron, because the little balls that you see moving around, the green, red, and blue, those are quarks. Those are not the neutron. The neutron is the whole thing. It's the whole ball. And so the question is, why don't those quarks, why are they trapped inside there? Why don't they just fly out? What's keeping them there? Okay, we need to understand that as well, because they kind of artificially put that region around it, that membrane that the quarks are trapped in. And the question is, what is that membrane? The membrane itself, because the quarks, the 3 quarks make up the neutron, but what is the membrane that the jail that they have that contains them? That's what we need to answer, okay? So that's the first question I want you to keep in mind today. Here's a neutron versus a proton. You can see it here. Yeah, you can see the one is 2 ups and 1 down. The other one is 2 downs and 1 up. Great. And then you see all these little marbles going between them. And the question, and you can see this white path or street in which the marbles are playing there, And so the question, we need to find out what those are. And the marbles are going to be known as gluons, okay? And these gluon marbles. And then the white path that they're on, and that connects all 3 quarks, we need to figure out what that path is. Are those part of the standard model? Are any of these part of the standard model? Well, the quarks and gluons are, but the path there, the white part that's in the background where the marbles are rolling around, that part, I haven't seen it anywhere in the standard model. So that's one thing that we need to figure out. What are these people putting in there by hand without explaining where they got that or why it's there, okay? They kind of put stuff in there, and they just keep talking about gluons when we're concerned about, what keeps the quarks from flying away. Okay? We're talking about physics here, right? Okay, and so here, this is how they explain it. This is how a proton turns into a neutron and vice versa. And if you watch, you can see, there's some transfer of what is known as a pion, okay? And it converts one of the ups to a down, and then vice versa. It takes that down and turns it into an up. And, they just keep changing these back and forth. That's the process. There's no explanation for this. In other words, they just say, it is so. And the reason there's no explanation, this is just a mathematical trick. That's all it is. It's math, okay? They say, look, if we can change one of the ups to a down, right, you get a neutron. If you take one of the downs turning into an up, well, then you get a proton, okay? And the reason for that is they say every 15 minutes, okay, every 15 minutes, a free neutron turns into a proton, or you could say an atom, and vice versa. Okay, so all these free ones, apparently they have a morphing happening to them, and they morph into something else. They morph from a proton to a neutron, and vice versa. But what's the issue? The issue is that a neutron is neutral. That's why it's called a neutron. It doesn't have a positive or negative charge like the proton and the electron have. And so the question is, what happened to the charge? Okay, I mean, if you take the electron, negative electron charge, and you mix it up with a proton charge, both of them have 1.6 times 10 to the minus 19 coulombs, but in opposite directions, one is negative, the other one's positive. When they come together, they neutralize each other, and now you have a neutron. Okay, so it means that the electron had to bombard the proton in order to make that atom neutral and turn into a neutron. Okay, that's more or less what's going to happen with these neutron stars. They say the gravity is going to not even crush them, because even that's not true the way they explain it. It's not that it's compressed, okay? The way it works is this thing travels at the electrons and the protons are traveling at great speeds, and they're going one direction or another, and they collide. So it's not like they're squashed together, they collide. When they collide, well, they turn into neutrons, okay? And again, as that thing gets smaller and smaller and smaller, I guess the distances are smaller and the speed of these things are greater, and so they keep smashing against each other and forming these neutrons, eventually turning into a neutron star. Okay, that's more or less the process they have in mind. But here is, you just saw the pion over there going to the other side and turning one neutron into a proton and vice versa, and here you have, what are these pions? Well, and they put it with the letter pi, the Greek letter pi, that's why it's called pion. Muon is the same thing with the letter mu, okay? Pion consists of a quark and an antiquark. Great. Pions decay into muons, okay? Muons exist for only 2.2 microseconds before they decay into an electron and two kinds of neutrinos. And here you can see at the bottom, what they're talking about, this decay. And they say it just is. There's no explanation. You don't see the balls and how the ball really changed from one to the other. Just they look at mass, and they see something fly out, and they say, we'll call that Joey and Charlie. So Joey and Charlie flew out. They just give them names. Then they say, go look for them, to the guy at the lab. And meanwhile, they say, okay, we've proven, proof. We've proven that the pion decays into a muon. And here you see the muon decaying into an electron, okay? So you see the letter mu, in the first case, pion turning into a muon, and they have these bed springs there that we have no idea what they are. They just say, look, it's some kind of energy. It's a bed spring energy, and this energy goes out there and makes these changes. How the energy does it, we have no idea, because energy is a number. It's a value. And so to say that a number changes something physical into something else, well, we haven't learned much, especially about mechanism. So they have these ridiculous things invented by good old Richard Feynman, and known as Feynman diagrams. And you see how they, using this nonsense, this poppycock, this description, they convert pion into a muon and a muon into an electron. Plus some other debris there, some garbage that they put in there, which is just names that they invent. That's all it is. Okay? And then they say, well, we'll see if we can find it. give us more money so that we build a bigger collider and we'll smash it and we'll find out, what these other neutrinos and whatever are. Okay, so here you'll hear from the horse's mouth. Here we have someone from the establishment tell you exactly what I've just told you. So here it goes. Listen carefully. Here it goes.
The particle that mediates the strong force is the gluon. Now, gluons bind quarks together by constantly exchanging color charge between them. Gluons mediate the strong force, analogous to the way photons mediate electromagnetic force. Very simply stated, it is this constant exchange of gluons carrying the color charge that causes the quarks to stay bound to each other. This exchange occurs continuously, but you should know that this is happening so fast and continuously that there's no distinct gluons that could be detected. The constant exchange of gluons creates a kind of continuous bridge between quarks called a flux tube.
So that white stuff that you saw earlier, those bed springs, those are the gluon tubes, the flux tubes. Now the funny part about that is the word tube is a physical object. The word flux is a verb. So they put, they needed to cover all bases, so they said it's a flux tube. Okay, a flux tube. Why? Because they want to say both things. They want to say it's an object, it's a bed spring, a solid bed spring that prevents the quark from flying out, but it's a flow of something. Of what particles? As you can see, they put little sandstones there, and they have all these little marbles moving around. And each one is a discrete one. So, I don't know how these discrete little balls, which is what they look like, pulls. I mean, a bed spring can pull, but these are not bed spring. The bed spring is the road, and that's the tube. But the flow part is the little particles that are moving around. So is it flow or is it tube? That's the question. And it's a flow tube. So they were able to cover both bases with a flow tube. Okay, that's what a gluon is. Okay, so we have a flow tube, and here we have to look at this, which is the planetary atom that they start out with. And this was invented by these two fellows, Niels Bohr and Ernst Rutherford. And what it is essentially is you have a nucleus, okay, and it's orbited by an electron bead. That's how simple the hydrogen atom is, the simplest of all atoms. And over time, they invented those quarks that you see in the center. And you can see a little bit there, the bed springs that keep them tied to each other. And those bed springs are these flow tubes. So yeah, they have the flow in the tube. That's how they had to do it. Okay, and then the quark and the gluons themselves are really marbles, and they don't put them there because you wouldn't understand why the three quarks don't just fly out. And then you have this other ball that's covering them, the red one, the membrane there. And what is that? Well, that's in this case the proton. Because this is two ups, one down. But if you have two downs and one up, you get a neutron. And the question is, what is the membrane? What is the red membrane? They just put it artificially there. Okay? And I challenge anyone to take three balls, right, and make a sphere or a circle with it. And I'll bet you can't do it. Not with three balls. Okay? So that's the problem. They had to put it by hand, and so they just go in there and put a membrane around it, and it says, okay, I can see why the quarks don't fly out because they've got this prism that's encapsulating them. Yeah, but what is that prism? What is that that ball, that membrane? Okay, so this is the quantum proton here. That's what it looks like more or less. You have the orbiting bead. The proton is the one in the center. It's made out of these quarks, three of them there. And you have these energy levels or orbitals, whatever, that the electron rolls around and just falls back and forth between these energy levels. What is the neutron? Well, to look at the neutron, it's more or less the same thing, but we got to smash that electron ball, okay, the electron bead. We're going to smash it against the proton, okay, against those three quarks, I guess. I don't know if it's on the inside or on the outside, but here, I'll put it on the outside because nobody does it properly out there. and there you see the quarks, and the electron bead is right up against the proton. Now the electron bead is a little bigger than they usually say it is. It's 1,800 times smaller than the proton, okay, or less heavier, right? Which would indicate that it's probably smaller, a lot smaller, 2,000 times smaller, okay? But there it is. The electron bead is going to be smashed against the proton. Maybe it's on the inside of the proton, maybe it's on the outside. I put it on the outside because nobody else tells us where to put that electron bead. They never illustrate this stuff, and that's why you have to guess. And that's your neutron there, okay? Because once you put the negative electron bead with a positive proton bowling ball, what you get is a neutron. A neutron means it's the same mass more or less as a hydrogen atom, but it's got no charge. Okay? That's the difference. Okay, so this is what they're going to try to do. This is what they have in the back of their minds for neutron stars, because they're really going to squash the electron against the proton. Okay, not going to let it move anymore. It's just going to be squashed and squashed and squashed. And again, they don't talk about pressure, about squashing. They talk about speed of light and the fact that the electron smashes against the proton, and not that they're squashed together by, gravity, whatever gravity is, right? Okay, here you have another version of all this. This is how they construct these neutron stars, or magnetars, or any of those. And this is my version of the atom, so you can compare against the quantum one there. And this is the construction of our atom. It's a little different than the bead rolling around the nucleus. What you have is threads, two twine threads coming from every atom in the universe. One of the threads goes through the center of the atom, the other one goes around, okay, and builds the electron shell or membrane that encapsulates the proton star, okay? And that's essentially our atom there. What does our atom look like after a while? Well, after every atom is built, it looks more or less like that. Okay, that's our atom. Okay, and so what are we talking about? We're saying that the atom is not really a little bead, electron bead, rolling around a nucleus, right? We're saying that what we've been having all these years is actually a little ball, little fuzz ball, a little ball of yarn, so to speak, and it encapsulates a proton star. And in the center of that star is very dense, with threads from every thread in every rope in the universe, every atom in the universe that is connected to that atom. All atoms in the universe are connected between them. Everyone is connected to everybody else. Every atom is connected to everybody else, to every other atom. And here we have, again, this is how we build our neutron. Okay, here it goes again. We have the proton. Proton has that electron shell encapsulating it. The neutron is the same thing. We're just going to draw the artificially the same region, but the neutron is not encapsulated like the proton is. So we have the proton, which has that electron shell encapsulating it. The neutron is just a crossroads of ropes, and there is no shell there. We just put it in there by hand just to show you the same size of the proton with a neutron. Okay, so that's the only purpose of that circle around the proton, around the neutron. Okay, so here's how we construct the neutron. Why do we have that kind of neutron? Well, because we have every atom in the universe connected to all other atoms in the universe, and those ropes crisscross somewhere. And right there in the center, that's where we have our neutron. And again, there's no circle around it. We just put it in there to show you what the regular atom would look like, and that's more or less the volume that we look at when we talk about the neutron. Okay, that's all it is. So again, every atom in the universe is connected to all others, and there's regions where all these ropes intersect. Everywhere in the universe, there's got to be gazillions of these, and we call those neutrons. Okay, so that's what a neutron is under the rope model. That's how we build it. It's not a little ball that has electron beads squashed against the proton bowling ball. That's not the model. Model is what you just saw. Okay, and here you see how a proton turns into a neutron and back through beta decay. And here you see the neutron, and here's the proton, and you're going to see how the threads from the inside just come out and turn into a neutron, okay? And how vice versa, how the neutron also converts into a proton, meaning proton with an electron around it, meaning an atom, a hydrogen atom. Okay, so it's that's our model for beta decay. Okay, here it is one more time. You can see how one turns into the other. There's a neutron, and then now the opposite direction, it turns into an atom. Okay, and that's why the neutron and the hydrogen atom have more or less the same mass. Okay. Also, because most of the masses in the proton, neutron, and proton more or less have the same mass. Neutron is a little higher, just a tad higher. Okay, so here's the construction of a neutron star. We have first the explosion. We have a very dense star, very heavy star. This is according to the establishment, by the way. And there's going to be an explosion known as a supernova, okay, and it leaves behind, this little dot, this little ball, okay, and then that ball that's in there is perfectly round, or more or less, I guess it's approaching as round as possible and smooth, and it's all made of neutrons. Okay, that means that all atoms have been converted into neutrons, meaning that all the electrons have been squashed up against a proton bowling ball, and they have no place to move. Okay, so it's just a solid ball made of neutrons. That's all it is. Okay, these neutrons, pulsars or magnetars, they all have the size of maybe a tiny city. Here is one of these in comparison to San Francisco. Okay, so you can see more or less how big one of these neutron stars would be. It's about the size of San Francisco. Okay, this is what they say it is, a few kilometers, in diameter. That's all it is. And of course, this means that we cannot see it because, you're trying to look at the city of San Francisco in another galaxy. What chances do you have? None. Absolutely none. So let's get one thing straight. They've never seen, let alone a black hole, they've never seen a neutron star, they've never seen a pulsar, and they've never seen a magnetar. And you say, well, how do they know they exist? Well, because, again, there's this beacon, this lighthouse effect, where there's a light that somehow passes through the Earth every so many minutes, every so many seconds, every so many hours. And they say, what's there? Well, it's got to be one of these neutron stars that's twirling on its axis, and it's got this flashy light that reaches the Earth. Okay, so that's how they detect this stuff. And here you see it. Here's the pulsar, okay, or neutron star. It really doesn't matter, and it just wobbles like that. And so you can see it sends all these beams outwards. And so when they put their telescopes, their high-powered telescopes, they can see some of this light flashing every now and then into their eyes. Okay, so that's how they claim they detect it. These pulsars or neutron stars, they also have great magnetic fields, strong magnetic fields, the strongest in the universe, they say, which really cannot be true because black holes are, I guess, would have stronger magnetic fields than these. But again, black hole is absolutely nothing, so I doubt very much it's got even a magnetic field if it's nothing, but they say they do. And so the question is whether a neutron star or a black hole has a stronger magnetic field. Okay. And the funny part about this is they get rid of the magnetic field completely. They don't have any use for it whatsoever. All they say, oh, it's got a magnetic field, how nice. And then they continue talking about gravity. They only talk about gravity, okay? And so the only purpose of this pulsar or neutron star is to show that gravity is what moves things in the vicinity around. They can't see this neutron star. They can only see a flash every now and then they see some action, some whirlwind, maybe some gases twirling around or some stars moving around. They say, oh, it's caused by that thing that we can't see that's in the center. That's more or less the situation. And then they make a computer simulation of that, and that's what they show you. Okay, but they've never seen any of these monsters. Okay, so let's get that absolutely straight. Okay, so how do they detect them? Well, here you can see they say this is what they see. And again, this is a computer simulation. This is not a film of the sky, okay? It's a computer simulation of what they more or less, they say this is what they see in the night sky. They see a very faint light in the way out there in the distance that is, on and off constantly, turning on, turning off, turning on, turning off. And so, yeah, it's titillating. And so when they see this, they say, oh, we know, that's a pulsar, okay? And depending on how much mass it's got, they can talk about whether it's a pulsar, if it's got a strong magnetic field, it's a magnetar, and so on down the line. Okay? So this is how they categorize these things. What it amounts to essentially is that all these people are stamp collectors. That's all they do. They just have this little book and they put names and collect all these little names, put them on a book, and they say, oh, this is a magnetar, and this is a pulsar, and this is a neutron star, and this is a black hole, and so on. And they've never seen one of these. Not the real thing. Okay, so they're speculating that what's happening in there is that light, that beacon that's moving around, that's caused by a neutron star or one of the others. Okay, so here's the sequence. Okay, so that you can see it. First, the step is for the formation of a neutron star is the inner core of a massive star begins to collapse, or the whole thing collapses upon itself. And you can see there gravity smashes electrons and protons together, forming neutrons and releasing a shower of neutrinos. Outer layers slosh violently from standing accretion, shock, instability. In other words, what they say is what you're having is gravity pulling on every atom on the surface. It's pulling where? Towards the center of that object, the star. Okay, but it's not massive enough to be turned into a black hole. It's going to turn into a neutron star. There you see the outer layers bounce off the dense core, creating a supernova. That's going to be the explosion. Okay, and the inner core implodes under gravity. Outer layers implode and collapse onto the inner core at 25% of the speed of light, and the resultant free core is a neutron star. Okay, I think I got the numbers in reverse, but I guess you see the notion there. It's I guess the 4 is number 2 and so on down the line. But the point here is that what you have is gravity pushing inwards towards the center of the star, pulling really every atom on the surface inwards, okay, until the thing eventually explodes. And when it explodes, what it leaves behind is this little ball, right, size of a city, New York, San Francisco, so, or even smaller. And here you see the internal part of this neutron star, okay? And what do? You see that they have no idea what's in the center. They have all these outer layers, and they say that they are able to predict, as they call it, calculate what each layer should be composed of if it's made out of neutrons. But the inner layer is what they don't have any idea of. That's quite interesting. They still haven't developed the math to tell us what's in the center. Okay. In fact, here I have someone who tells us what the formation is, so that you hear it from the horse's mouth. Okay, here it is. Let me show you. Listen carefully. Here it goes.
A neutron star forms when a massive star's core runs out of fuel. With nothing left to fight gravity, the star collapses. Here, protons and electrons crush together to form neutrons, as well as lightweight particles called neutrinos that escape the star. The core continues to collapse until the matter at its center has twice the density of an atom's nucleus, but on a city-sized scale. When the core can't compress further, it rebounds. The expanding core crashes into the star's collapsing inner layers, creating a shockwave that rips outward through the star. The result is a powerful supernova explosion with a newborn neutron star at its center.
Okay, so you can see how it's formed. That was, again, a computer simulation of what they think is happening. They say all these things explode, and what's left behind is a little ball. Okay, but here's someone who tells you what the interior looks like. And again, No clue whatsoever what it looks like inside the center. Listen carefully. Here it goes.
Still, the nature of the ultra-dense matter in the cores of neutron stars is unknown.
The nature of the ultra-dense matter in the cores of neutron stars is unknown. The nature of the ultra-dense matter in the cores of neutron stars is unknown.
Okay, this is what they see out there with their telescopes, or again simulation. They see something like this. Okay, and actually it looks quite a bit like when they do these things. What they're really saying is that they're talking exactly what they would say about a black hole. This is more or less what they see, that the neutron star or pulsar or magnetar, it just collects gases from another star, forces them to twirl around, and does all these fancy things. They don't see the thing in the center. What they see is the effect. They see gases being sucked for some reason, and they see all these jets coming out of that thing. This is exactly what they show for a black hole. And the funny thing is they can't see these things either, so there's really no difference between a neutron star, pulsar, magnetar, or a black hole, because they can't see the thing in the center. All they can see is the gases swirling around, the jets, the visible stuff. And so the question is, do neutron stars really exist? Are there such monsters, such heavy monsters out there in the night sky? Are there pulsars? Are there magnetars? Well, again, it's like they're looking for angels. They're looking for spirits out there with their telescopes. And all they can do is speculate. And again, it's based on an irrational notion. And the irrational notion is carried to its full extent with a black hole. Black hole has crushed all matter out of existence. There's a contradiction between that and saying it's got infinite mass or whatever, because if it's crushed all matter out of existence and it has no size, no shape, no length, width, or height, or whatever, then it's got nothing. What you're talking about is absolutely nothing. And this neutron stars are a little more than nothing. They're a little more because they have something. And they say there is something there. It's the size of a city. We can't see it. We don't know what it looks like. It's got to look like a ball. If it's made out of neutrons, they're all packed together. And this thing is sending us these signals to our eyes. And so, yeah, what we do here is we can only put our version, and my version is out there, and you'll see it. You can look at a playlist that I've got up there at the top of my channel. It says Death of Black Holes, and you can see it there. But here is just a summary, and we're saying it's a magnetic field kind of problem. Okay, what you see is a star moving around because something is compelling the star, a visible star, to move around. And what is it? We're saying it's the magnetic field of the galaxy. And those are the jets coming out of the north and south pole. Okay? Those are jets. Those are the jets they say belong to black holes. No such monster in the sky. So they're not jets. What they are is magnetic field of the entire galaxy. What are those? What is a magnetic field? Well, it's made out of threads, gazillions of threads coming out of the center of the galaxy and going around the galaxy and coming back, you could say, through the south pole of the galaxy. Okay, so it goes up the north pole and also up the south pole. That's what we're saying. And all these threads are going around, swooping around, swinging around, and by doing so, they have the power to move a charged object such as a star around. Okay, so that's our model. You can see it better in the channel there, Death of Black Holes. If you want to get a better feel for what I'm talking about, this is just a summary here. But yeah, otherwise you would have to think that, okay, if gravity does it, what's the mechanism? I have no problem with them saying, look, it's gravity. Okay, so it's gravity. We'll concede. Show me the mechanism. How does a star affect one far away, force it to go around itself, suck all its gases, or do all these fancy things from a distance? Tell me, what is the mechanism? For the mechanism, you had better put something between the black hole, neutron star, pulsar, or whatever, and the star, the visible star. There's got to be something there. Otherwise, you're going to be doing it with black magic, witchcraft. So you have to put something in there to show me a mechanism. You can't just say mass does it, gravity does it. You haven't said anything. Because all you said, there's this concept that you know nothing about, and you call it gravity. You could have called it Charlie for all we know and say Charlie did it. Okay, so what's Charlie? You got to show me Charlie, and here you got to show me what mass and gravity are, what mediates mass and gravity, and only then can we understand how a black hole, a neutron star, a pulsar, or whatever affects a star, gazillions of miles away from it. That's the only way.